I'd like to welcome you to the first Glenn Knoll lecture to be presented by Dr. William Moses. My name is Ron Gilgenbach. I'd like to say a few words about Professor Knoll. This annual lecture series was made possible by a generous endowment made by Gladys Knoll, who's in the back row. To commemorate the over 50-year UM career in education and research of the late Professor Emeritus Chair and Interim Dean Glenn F. Knoll. These lectures in nuclear measurements, the field pioneered by Professor Knoll, will be an inspiration to future generations of students. So it is fitting that I tell the younger members of this audience about the inspiring career of Professor Glenn Knoll. Glenn received his MS in Chemical Engineering from Stanford in 1959 and his BS in Chemical Engineering from Case Western Institute of Technology in 1957. He served on the NE faculty for over 50 years as chair from 79 through 90 and as interim dean of the College of Engineering from 95 and 96. He authored or co-authored over 200 technical publications, 7 patents, and 2 textbooks, including his classic book, Radiation Detection and Measurement, now in its 4th edition. And I'm sure that all the students and faculty here have studied from this book. Glenn was one of the pillars in the foundation of the NE department at UM. When the department was founded, there was no well-defined field of nuclear measurements. Glenn changed all that with his pioneering research culminating in the publication of that classic book. In 1999, he was inducted into the National Academy of Engineering. In 2000, he received the highest faculty award from the College of Engineering, the Stephen S. Atwood Award. He was a fellow of the American Nuclear Society, the IEEE, and the American Institute for Medical and Biological Engineering. He received many other awards, including the Glenn Murphy Award, the Arthur Holly Compton Award, 2 major awards from the Institute of Electrical and Electronic Engineers, and served as the editor of Nuclear Instruments and Methods in Physics Research, Part A, from 1995 until several years ago. It would be impossible to list all of Glenn's accomplishments today, but it would be fair to say that Professor Knoll has in large part made the NERS department and the field of nuclear measurements what they are today. Most of all, Glenn's absolute integrity and uncompromising standards of excellence have deeply impacted all of us. I truly believe that the NERS department's #1 ranking over the years was in large part due to Glenn Knoll's reputation, even after his retirement. And I'm pleased that this month we will begin construction of the Glenn F. Knoll Nuclear Measurements Lab, also funded by Gladys. Glenn was a great leader, co-worker, mentor, and most of all, a friend to all of us. It's an honor for me to introduce this lecture commemorating Professor Glenn F. Knoll. So, now I would like to introduce our speaker, Dr. William Moses from Lawrence Berkeley National Lab. Dr. Moses received his bachelor's degree in physics from Dartmouth College and his PhD from the University of California, Berkeley. As shown in the slide, he directs a wide range of research projects that apply nuclear measurements to medicine. So please join me in welcoming Dr. William Moses.
Well, thank you, Ron, and everybody else. And I'd like to start out by saying what a real honor and privilege it is to have been selected to give this lecture. I feel lucky to have considered Glenn both a friend and a colleague for over 25 years, and would like to sort of start out with a little bit of a story about that, because my first trip to University of Michigan was to a conference that Glenn organized about 25 years ago. And that was my very first presentation, oral presentation at any conference, anytime, anywhere. And here I was, this kind of wet behind the ears postdoc, giving a presentation for the first time. I knew who Glenn was. He had no idea who I was. And gave the presentation, and afterwards Glenn came up and started chatting, and chatted about a number of things. And in fact, he invited me to a barbecue that he was having for the people who had organized the conference right after the conference was over. And so really that was, and at this time, I don't think he was quite the dean yet, but he was certainly chairman of the department. And that's, I think, just very typical of Glenn. He always treated me like a colleague, even though, or like an equal, even though he was far senior to me. He always treated me as a friend and an equal, and I really appreciated that, and I strongly suspect that was just Glenn. I strongly suspect that everybody here that interacted with him probably got treated exactly the same way. So, okay, so I'm going to start out not assuming that people in the room don't necessarily know about PET, about positron emission tomography, go through it fairly quickly. PET is something where the patient is injected with 511, or with a drug that's labeled with a positron emitter. And that drug localizes wherever in the patient it does, depending on the biological properties of the drug. For example, there are drugs that localize in tumors. And the radioisotope decays emitting a positron, which then very quickly finds an electron from the tissue, and it forms back-to-back gamma rays. And these gamma rays are detected via time coincidence. You put a ring of detectors, gamma detectors, around the patient. Each detector identifies an individual gamma ray using time coincidence, and then you know that the radioisotope, the drug, lay somewhere on the line connecting those, and then you reconstruct the image using computed tomography. And this is a fairly common thing done. About 1 million studies a year are done in the US. The most common use for it is in cancer and oncology. Like I said, there's a very common drug that goes to tumors. Like this breast cancer patient here has quite a few tumors inside before chemotherapy. After chemotherapy, you see a much cleaner picture. And the drug doesn't only go to tumors. This drug also happens to go to the brain, it goes to the heart, and it goes to the bladder. So it's a very good way of seeing what's going on inside the patient and the biology that's going on inside the patient, and seeing whether they're responding to treatment. However, one of the things about PET is that those gamma rays have to go through the patient, and the patient is an attenuating material. So if you have a slim patient, they have a lot less material that they have to go through than a large patient does. And so the image quality that you get in a small patient is significantly better than what you get in a large patient. And for basically if you go from a 60 kilogram person to a 120 kilogram person, you'd have to basically put in, more than twice the amount of drug or scan for more than twice as long in order to get an equivalent quality image. This is a good way of physicists thinking about biology, thinking about patients, trying to assign a diameter to a patient. You can do it sort of a reasonable way, but the point of it is that there's a pretty wide range of patient diameters, and patient diameters can get pretty big. Even, kind of in the normal range here, there's a kind of a 50% range, and you can get diameters that are above 36 centimeters. And this is not confined to the United States. This is from the Netherlands. I love this quote. Dutch hospital beds and operating, the doctors complain that Dutch hospital beds and operating tables could buckle under the strain of obese patients. Doctors have complained, adding that some patients barely fit into the scanning machines. This is truly impressive. The scanning machines have about a 60 centimeter diameter patient port, and not being able to fit in that is quite something. So a good thing is that there's something called time-of-flight PET. that can improve that. In normal PET, you can only constrain where the radioactive drug is to a line connecting those two detectors. But if you do a good job of measuring the time, the arrival time of those two, you can constrain where it lies to where the drug came from to a line segment that is in there. And by doing that, it actually reduces the noise in the image. It doesn't improve your spatial resolution, but it improves your noise. And the amount that it improves the noise by is the ratio, the diameter of that object to the size of the line segment that you can constrain it to. And so we'll talk about how that happens on the next slide. But what that means is that you get the biggest improvement in large patients. So basically, you get the biggest improvement where you need it the most. So how does this happen? How does noise, how does measuring time reduce the noise? Well, I think we've probably had enough basic physics and statistics to know that if you put a point source in the camera or whatever, and you measure n counts coming out of that, n radioactive decays, that your signal is going to be n and the noise is going to be the square root of n. And that is absolutely true if you've only got radiation in one voxel in the image. But the thing is that the fundamental measurement that you make in PET is not how much radiation is in that one voxel, but how much radiation is on the line connecting to detectors. So if I've got radiation in another voxel, that adds to what I'm observing, the signal that I'm measuring inside that line. And therefore, the statistical fluctuations from this voxel add to the statistical fluctuations in that voxel. And so when you go and you reconstruct the image, well, so, and basically, so when you go and reconstruct the image, this no longer holds. It degrades, the noise is amplified because you've got a bunch of other voxels that are contributing to the noise of this one. And of course, any radiation in any voxel anywhere in the camera, there is a line that goes between that voxel and the one that you're looking at. And so this voxel is getting noise from all over, from any place that's emitting. However, if you're able to measure the time of flight, you can pretty much put a ring around that. Noise from voxels that are far outside of that, ring don't contribute to your statistical noise anymore. And so basically, you are reducing the amount of noise in that voxel. What can you reduce? What can you do with that reduced noise? You can reduce the scanning time. You can scan for the same time and get a better quality image. You can reduce the amount of dose that you're injecting in the patient or some combination of that, and it's all good things. To get an idea of how this may, visually how it will work, we take a phantom called the Zubal phantom. This is kind of like a cross-section through the abdomen. This is supposed to be the body, this is supposed to be the liver, and that's supposed to be a tumor. Using normal PET image without using time of flight information, you basically have a really hard time seeing that tumor at all. And as you improve the timing resolution, you can see that the noise in the image gets better and better and better, and it makes it so that you can very clearly see the tumor there. And that's the time of flight PET is something that people realized potentially was doable a long, long time ago. However, it never really became mainstream until recently. And the reason was, at the time that kind of PET was developed and the first time that time of flight PET was considered, the materials, the technology that was available to people at the time just wasn't good enough. It had a lot of other problems that the ones that could do the good timing had problems in other areas. More recently, some scintillators have been developed that can provide the time of flight information without the other drawbacks. A lot of other improvements have happened since the 1980s, and so there's really been a rebirth in thinking in time of flight in the last about 10 or 15 years. And so starting about 10 years ago, perhaps, was the first commercial time of flight PET camera came out. Now all of the major PET camera manufacturers offer a time of flight PET camera. They all use LSO or LYSO scintillator crystal. They have the timing resolution is getting better and better, but it's still in the sort of 500 picosecond-ish range. And a research camera was built with lanthanum bromide scintillator. Its timing resolution is a bit better. And here's an image from a time-of-flight PET camera. One of the things that's kind of cool, too, is you can take the same data, you can ignore the good timing information, and you can reconstruct one image, and then you can take that exact same data and reconstruct it with the time of flight and do a very good comparison of the two cameras, and you can really see what the difference between including the time of flight is. And I think it's very obvious that the image quality here is significantly better than the image quality there. You can see some tumors that were perhaps not visible up here, and you can see, for example, this spot up here, which although you can see, you can kind of see down here, well, maybe that's actually two different tumors down there. So it works. Okay, now we've achieved a time-of-flight PET camera. How can we make it better? Because the improvement is the size of the object, which we'll call that fixed for right now. That's a patient, divided by basically multiplied by the timing resolution. So make a smaller timing resolution, you get a better camera. So if you look inside of a PET camera, the detector module looks something like that. You have a bunch of individual scintillator crystals. Gamma rays interact in the scintillator. That energy gets turned into light. That light gets there's a light guide that sort of splits the light amongst two photomultiplier tubes. Those take the light, turn it into electrical signals, and then is read out with electronics. So that's standardly inside of a PET detector. What are the things that are affecting the timing resolution inside of that? One of them is just the geometry of the scintillator crystal. If I take a small piece of scintillator and put it to a photomultiplier tube, the light has to travel different path lengths depending on the direction that the scintillation light came out, but those path lengths are all fairly short, and the difference in time between them is fairly small. If I've got a long scintillator crystal, which is what we have in PET, again, there are a number of different path lengths that the light can take in order to get from the interaction point to the photomultiplier tube, and there's much more path length difference between those, and that will cause a degradation in the timing resolution. I also said that we used light sharing in order to decode which one of these crystals the interaction took place in. And I think it's kind of obvious, too, that the path lengths that the photons take to go from the interaction point to the photomultiplier tubes get kind of elongated, made longer, more variations in that from that light guide, that light sharing. The photomultiplier tube also, the characteristics of that affect the timing resolution. So the photons hit the front face of the photomultiplier tube, and sometime later an electrical signal comes out. And if you kind of plot the time that it takes, the difference between the time that the photon hits the front of the photomultiplier tube to the time that the electrical signal comes out, that average time difference is called the transit time, but not every single photon makes it through the PMT at the same time. There's jitter, and that's called transit time jitter. And so the variations in transit time make a difference, and the transit time jitter also degrades the timing resolution. This is supposed to be the surface, the front face of a photomultiplier tube. This is crystals, putting a scintillator crystal on different positions on there, and measuring the top number in there is the time resolution of the exact same crystal put into on different positions on the photomultiplier tube. And to make things a little bit easier, I have highlighted the lowest number and the highest number in red. And the point is that the timing resolution varies depending on where in the photomultiplier tube you put that crystal. And the lower number is that transit time. And again, the lowest number and the highest number are shown in red. And again, the time that it takes to go through the photomultiplier tube varies from on position. So you need much better uniformity in your photomultipliers in order to improve the timing resolution. Excuse me. So, kind of putting that all together, we sort of went through and tried to actually quantify what is the differences in time, or what are the contributions that each of those things are making to the measurement time. And it turned out that a lot of it was in the photomultiplier tubes. And changing the photomultiplier tubes was something that you could do relatively easy. Better photomultiplier tubes were available, they just cost a bit more. And so when the manufacturers pretty much changed the photomultiplier tubes, their timing resolution went from a bit below 800 picoseconds to a bit below 600 picoseconds. There's not much that can be done about this part, though, without completely changing the geometry. And right now, most of the PET cameras, commercial PET cameras, are still using this type of geometry, and therefore they're likely to be stuck around this number until they do some sort of a design change. So one of the things that we then did was try to do a design change, just to see how good you could get timing resolution. It's not necessarily commercially viable, but it's something to do to see how good it is. So the normal geometry is that the photomultiplier tube is coupled to the small side of the crystal, and the gamma ray is coming in like that. And again, that causes some timing variation because the different path lengths that the photons have to take to get to the photomultiplier tube, that there's a lot of path length difference there. If you take that exact same crystal and instead of coupling to the end, couple the photomultiplier tube to the side of it, the photons have to travel a much shorter distance, and therefore the timing resolution gets better. And in fact, it gets rather substantially better, not quite a factor of 2, but pretty darn close to a factor of 2 better. So what we did was we made a camera based on that. Our detector module, here's a picture of our detector module. We put 2 crystals onto a photomultiplier tube. These crystals, there's a reflector between those 2 crystals, so they're optically isolated from each other. They're glued to the photomultiplier tube. And you'll also notice that there's this little open bit. No reflector material. That's the scintillator directly on the far side of that. And what that is for is to be able to sort of decode the crystals. This is kind of an exploded view. These, the crystals on this side, or the detectors on this side, are kind of pushed up like that. Really, these guys come down and fit onto here. And so if a gamma ray interacts in that crystal there, you will get a very large signal in that photomultiplier tube. Now, a little bit of the light is going to come out of that hole, and it's going to sort of shine on the edge of this photomultiplier tube. And so that photomultiplier tube is going to see a small signal. So basically, by seeing whether this tube fires or that tube fires, I can decode whether this crystal or that crystal is the one with the interaction in it. So we made a camera with this. This you can see the crystals and the photomultiplier tubes kind of push back together. They make, you zoom out a little bit, you can see they make a ring. You zoom out a little bit more, you can see a lot more of the ring and some of the electronics. And this is the completed camera. And we have completed this camera, and we have done, we're starting to do task-dependent evaluation on it. The whole purpose of this is not really, I mean, we do want to see whether you can get better timing resolution, but what we also want to see is what does that really buy you? Can physicians see tumors better using this camera than they could without the time of flight? And so we're doing this task-specific performance evaluation on it. But just to give you a bit of an idea, this is a phantom, a thorax phantom, reconstructed without the time of flight information, and this is it reconstructed with the time of flight information. And I think that there's a very significant improvement in the quality there, and also this timing resolution is the best timing resolution of any PET camera in the world right now. So, okay, we've now kind of looked at, sort of what PET is in general, why one might want to do time-of-flight PET, a camera that we built in order to try to get as good timing resolution as you possibly can. What we'd like to do now is get even better timing resolution. I'd really like to get probably a factor of 2 better timing resolution. And so how do we go about doing that? And in order to tackle that, what we really had to do was think about what are the fundamental causes of the timing resolution, and to try to understand what timing resolution we can really achieve. So this is kind of the signal coming out of a photomultiplier tube. The interaction occurs there. You get a large increase in your signal, and then sort of an exponential decay. And what you're kind of doing is you're kind of fitting to this leading edge there, and where it intersects 0, that is where you think that your interaction occurred, what time the interaction occurred in. However, there's usually a little bit of noise on that leading edge there, and so you can take the same data and you can kind of fit it different ways, and you kind of get different estimates of the time, and that is really where that's where your timing resolution comes in, is basically the variation in those different times. I think it's kind of obvious that you want to have a steep leading edge, because if a leading edge that is not quite as steep, again, you may have the same sort of variations in your estimates there, but that gives you a larger variation in the time there. And so you really want a steep slope here in order to get the best possible timing resolution. And I said that there are variations. The variations make it a little bit difficult. Just to try to show that there are these variations, this is the oscilloscope trace from one event. And we may think of when we sketch a scintillator, we're showing a very nice smooth curve here, but in reality, there are statistical variations in the arrival time of the various photons, and they're very visible on this part here, but they're still present here. They're just a lot harder to see because it's going up fairly quickly. So again, the signal from the scintillator looks something like that. we want to have a very high initial intensity there in order to get as steep a leading edge as you can get there. Now this, when we look at scintillators, we usually characterize them as an exponential decay. And it turns out that the steep slope here basically means a large initial intensity. Most of the time when we characterize a scintillator, we talk about its decay time, which is that tau, and we also talk about its luminosity, which is total light output, which is the area underneath that curve. And that's a product of tau and I0. So these two curves here both have exactly the same luminosity. They have the exact same area under the curve, but one's got a 25 nanosecond decay time, one's got a 50 nanosecond decay time. And obviously the one with the shorter decay time gives you a higher initial intensity. So you want a scintillator that has a very high initial intensity. In order to get that, you need a high light output and you need a short decay time. Looking at some of the scintillators that have been used in PET, there's the scintillator, the decay time, the luminosity, and there's that initial intensity. For a long time, BGO was the scintillator of choice, and you can probably see that that is going to give you really lousy timing resolution. Back in the 1980s, barium fluoride was the one that was most often used for time-of-flight PET. It had much, much better initial intensity. LSO was the thing that really enabled time-of-flight PET to come back to recent time-of-flight PET. You can see that it has substantially better initial intensity than BGO, but not quite as good as barium fluoride. Lanthanum bromide is an even more recently discovered scintillator. It has much, much better timing properties, although some of its other PET properties are not as good as LSO. Lutetium iodide is absolutely awesome in terms of both decay time and luminosity, really incredible initial intensity. Unfortunately, lutetium iodide is sort of unobtainium. It's a material that you just can't seem to grow in the large pieces that you need to in order to do PET. But basically, this revolution in the scintillators has been one of the things that has really fueled time-of-flight PET, and improving this initial intensity is really the thing that is going to get you the most in terms of your timing resolution. Again, this is kind of the same thing here. We zoom in on there, and kind of all of this part here is pretty much irrelevant to the timing resolution. This is what gets you for the timing resolution. So you can almost think of this as like a step function right here. You zoom into small times. There's basically no photoelectrons coming out here. Then all of a sudden you throw on a switch, and then it's coming out at 100. Not all of the photons that are produced by the scintillator survive in order to get measured. So what's really important is it's really the initial photoelectron rate, which is it's this initial intensity here, but it's also multiplied by the amount of energy that you deposit, how much of the photons, what fraction of the photons you collect, and what fraction of the photons your photodetector actually sees. So looking at a model where you sort of say, let's sort of throw the switch, and we go, we start at time 0, or we got 0 here, and we throw the switch, and we see lots and lots of photons coming out here. Now let's look at what time those photons actually get detected, and the jitter in that, and especially the jitter in that. So these plots here are showing the jitter in the first photoelectron that's detected, the second photoelectron, the third photoelectron, the fourth photoelectron. It's kind of talking about, you know, how much information is each photoelectron giving you. And low timing resolution is what you want. And you can see that those first couple of photoelectrons are really the ones that are giving you the timing resolution. So this is, you have to make a couple of assumptions in order to do this. I'm going to call this a poor time-of-flight PET detector. It's using LSO, and these numbers here are for not quite the best quality LSO. A photomultiplier tube that has pretty marginal quantum efficiency and about 50% collection efficiency. And you can still see that the initial photoelectron rate is about 50 photons per nanosecond, which is kind of like about 1 every 20 picoseconds, something like that. So pretty good timing. If I go for a good time-of-flight PET, a better scintillator, a better photomultiplier tube, better collection efficiency, you get more than 10 times that photoelectron rate, and you get incredibly low time jitters here, down in the order of a few picoseconds. So why am I talking about individual photoelectrons? Well, it's because most of the time the jitter in those individual photoelectrons is what kind of gives you your timing. Most of the time you put a trigger level there, the signal goes like that, and it's that jitter in that photoelectron that is giving you your time jitter there. The jitter in the arrival time gives you that time jitter there. And this is maybe the signal from one photoelectron. If another photoelectron comes along, again, if you hold this one still and move the arrival time of this photoelectron around, move your trigger level up like that, again, you'll see that this movement here is really what is giving you most of your arrival time variation. And this is what is often done, and this timing jitter analysis was first described by Post and Shift in like the 1960s. The problem with this is that it predicts absolutely incredible timing resolution. What I was sort of showing in the poor time-of-flight PET scenario, it is predicting 66 picosecond PET timing resolution. In the good time-of-flight one, it's predicting less than 5 picosecond timing resolution. What timing resolution do we actually achieve? Rather worse. And very, very significantly worse. 250 picosecond-ish as opposed to 66, 150 as opposed to 3.7. So what's going on there? Why is Post and Shift not doing the right thing? And the problem is that there are a whole lot of real-world effects. The signal does not just turn on instantaneously. It does not go from 0 to full speed instantly. There are a lot of different things that affect it. The scintillator does not emit light immediately upon getting struck by radiation. It takes a little time to turn on. The transport in the scintillator, we talked about that a little bit. That takes a little while to turn on. There are variations due to that. The photodetector has a rise time to it, so that means it doesn't turn on instantaneously. And there's that transit time jitter that we talked about, and that also causes problems. And then also the individual photoelectrons also overlap a little bit, and Post and Shift don't really take care of that overlap. So It turns out, actually, one thing that turned out to be very nice is the mathematical format of a lot of those real-world effects are identical to each other. So if you want to model this, doing the modeling using exponential rise times works well for all of those things. So basically, what we did was we went through and we modeled, we did Monte Carlo simulation that included all of those effects. And this is what we saw. So this is our kind of ideal situation where you throw the switch and it turns on. If you include 100 picoseconds of transit time jitter in your photomultiplier tube, it looks like that. It significantly slows down that rise time there. If instead of putting in transit time jitter, you only look at a rise time, 100 picosecond rise time, you get something that looks like the green curve there. And if you include sort of all of those effects, if you include 100 picosecond rise time, 100 picosecond optical transport variations, and 100 picosecond transit time jitter, you get this black curve here. And you can see instead of turning on immediately, this is really kind of looking far from immediate. Although I should say this scale here is 0.3 nanoseconds, which is a pretty short time. But what you're seeing really is that those instant photoelectron rates that Post and Schiff is talking about really don't apply here. And in fact, if I start looking at the first photoelectrons that are coming in, my photoelectron rate here is really very, very small. So what happens there, these graphs are perhaps a bit confusing, but this blue curve here is the ideal one. That is the perfect world with the instant rise. This one up here is what happens with the, when we include the real world effects, sort of all the real world effects. And you can see that the timing jitters for those individual photoelectrons are considerably worse than they are, and than they are when you don't include those effects. And so the conclusion of this really is that we do understand what those, why it is that we weren't getting those incredibly good timing resolutions. And we can also, it turns out that the experimental validation of that, if you look at what these simulations predict and what kind of timing resolutions you actually achieve, you actually get pretty good agreement. So we think that we've got a pretty good handle on what is really going into the timing resolution. So basically, what can we improve in order to get our, to push the timing resolution of PET even better? With the scintillator, we need a higher light output. LSO is most often used in PET right now, and it's only about 25% of the theoretical maximum. A shorter decay time is possible. For a cerium 3+ dope scintillator, which a lot of them are, that's pretty much close to the theoretical maximum right now, but there is a different class of solid state of scintillators called solid state scintillators that could possibly provide this decay time. The problem is it's really hard to get all of these properties and all of the other PET properties that you want in one single material, and people have been working on that for a while. And so if you're looking into the really short-term future, betting on a new scintillator really isn't, I don't think, is the right thing to be doing. For the photodetector, all the work I was doing previously was talking about photomultiplier tubes, which have a quantum efficiency of about 30%, and the best transit time jitters are about 200 picoseconds. It turns out that there's some new some new photodetectors that are coming out right now. The silicon photomultipliers, they're also called MMPCs or SPADs or Geiger mode APDs. There are a lot of different names for them. But the general idea, I don't mean for you to read and understand all of that, but the general idea is that they're silicon devices, they're solid state devices, and they're very small. And they also have very good, they have the potential to have very good quantum efficiency, although in the world of silicon photodetectors, they call that PDE. And they have very good timing resolution, and why they don't call that transit time jitter, I don't know. They call it SPTR. But those are really pretty incredible. So we ran simulations showing, trying to predict the timing resolution that you would get for various different, call it quantum efficiency and timing resolution. And this is kind of about the best that you can do right now. This is with a photomultiplier tube, and this is with a relatively small crystal. And people are getting about 100 picosecond timing resolution when they do that. And this is also about where silicon photodetectors are right now. They have silicon photodetectors with about 30% quantum efficiency and about 300 picosecond transit time jitter. If we can move down here to 50% quantum efficiency, 100 picosecond transit time jitter, we can cut that timing resolution almost by a factor of 2. And this is not out of the question. There are individual devices that have 50% quantum efficiency, and there are individual devices that have 100 picosecond timing resolution, transit time jitter. The problem is they're not in the same device. If you can put them into the same device, then there's a reasonable, and it's reasonable to think that you can do that. And if you're going to sort of look out, kind of 10 years or something like that, I think that it's possible to get quantum efficiencies in the 70%-ish range, and I think it's probably reasonable to drop that timing resolution, that transit time jitter, down by another factor of 2. And that would get you about 30 picosecond timing resolution, and that is really pretty incredible. And so how far do I think we can go? That 30 picosecond is for the timing resolution for one detector. So for PET, it's, you have to put them together, multiply by the square root of 2. So that's about 50 picosecond timing resolution. That'll give you about a 50-time increase in the variance. So current time-of-flight PET cameras right now improve the variance by about a factor of 5. This would improve it by another factor of 10, which is very, very significant. It also, if you think about it, it means you don't really need a reconstruction algorithm. 50 picosecond timing resolution, you're constraining the position of the positron to just, to less than 5 millimeters. So instead of having to do computed tomography to figure out where the, where the radiation was from, you can just take every single event and place it right at the right spot. And you put it all together, I think that would allow you to acquire and reconstruct an image in less than a minute, which I'd like to do that. So in conclusion here, I think that the benefits of time-of-flight PET are huge. You can get about a 5-fold improvement in the efficiency with timing resolutions that we can get today and are in commercial cameras today. It gives you the greatest improvement in large patients, which is where we need it the most. And I didn't really talk about this at all, but it makes it easier on the reconstruction algorithm. The more information you give to the reconstruction algorithm, the easier it is. I think that the rebirth of time-of-flight PET is due to new scintillators, that improvements were in new scintillators made that possible. And I think that 50 picoseconds is physically possible. I think we can do that. It's going to take a fair amount to do. It will take improvements in pretty much all of those categories in order to achieve that. But I do think that there's much more improvement to come. Thank you.
One of the benefits of that building is that because a reactor was there, and so a reactor is a radiation source, there are very thick walls that can shield this radiation and make the environment safe.